Okay, I guess we can start our session. Others will join with time. So my uh, so my name is Varnit Kapoor, and I'll be taking up this week 5 CFD using FVM lecture. So let's start. Let me share my screen. Okay, I think my screen is visible. Just let me check. Visible. Okay, so I guess my screen is visible. Yeah. So let us start for week 5. So in week 4, we did few problems, numerical problems, and we did discuss about different kind of boundary conditions. In the problem itself, we made the equations. So now, and we got some linear algebraic equations at the end. Now the case is that how you will solve those linear algebraic equations. How you will solve. So heading is solution of linear algebraic equations. I hope whatever I'm writing on the screen is visible. Okay. Now, solution of linear algebraic equation. So already it has been discussed about the Gauss-Seidel method in the previous lecture videos by the prof. And similarly, in this lecture, we will be discussing about one of the another scheme, that is PDMA. So suppose if we take a case of 1D diffusion, one-dimensional diffusion case. Okay. Okay. Let me turn on my camera. Okay, I am visible. Great. So solution of linear algebraic equations and one-dimensional diffusion case. One-dimensional diffusion. So there is a Gauss-Seidel method and Gauss elimination method. Okay, that has already been discussed. Kind of Gauss-Seidel is a kind of iterative method. Okay, so Gauss-Seidel has been already discussed in the previous videos, which is nothing but iterative method to solve. Okay, there you guess the values. Okay, initially, and then you update the values. Next is Gauss elimination method, which is a direct method. But another is the case which we have to discuss today is the Thomas algorithm, or you can say tridiagonal matrix algorithm, TDMA. For me, Thomas algorithm or you can say PDMA. So I hope everyone has watched the videos of the week lectures given by the prof. Okay. I'll just give the brief of what has been done in all of the Week-5 lectures. So as we know that how the equation is being formed after going through the previous tutorials, that a general form of the equation is nothing but if the P is the point of the consideration. So AP phi P is equal to A east phi east node plus AW node phi test node. Okay. Plus some B for some source term or something else. Okay. Or another constants. Okay. So if you have a suppose you can say like this is your point P, this is your test node, this is your east node. Okay. So that is P, E, and W node. So similarly, I can say I can denote this P node as I, this node as I plus 1, this node as I minus 1. Okay. So I'll write it in the way A of I, phi of I, or you can say T of I. T is any property. Suppose T is equal to phi. Okay. A of I, T of I is equal to east node. Okay. And this node. So instead of A, I'll write here Bi, Pi plus 1 of the I plus 1 node, east node, plus Pi, Pi of Pi minus 1, west node, plus Di. So these coefficients are for the ith node. Okay. This is the value which we need to get at the ith node. These are the neighboring nodes for it. I plus 1, I minus 1. Okay. All right. Now, so I can vary from 1 to n. I can vary from 1 to up to n, where first and n is the boundary node. This and this are the boundary nodes. Okay. Right, like this, n minus 1 comma boundary nodes. These are the boundary nodes, and these are the 2 to n minus 1 are nothing but internal nodes. Internal nodes. All right. These are the boundary nodes. These are the internal nodes. Okay. Now suppose I give the boundary condition which we have already discussed as a Dirichlet boundary condition. The boundary condition. Example, I give the boundary condition as Dirichlet boundary condition. That is T at I, or sorry, T at first, T at the first node is known. So the first that is the boundary node is known to you. T1 is known. All right. Now, if you see, then from the equation, this equation, if I put I as 1 in the above equation, I is equal to 1, the equation will be A1 P1 is equal to B1 P2 plus, that is the east node, C1 west node, that is nothing but 0, plus how much? Plus B Di. Di is nothing but D1. So if you observe from here, C0 or C1 will be 0 because there is no T0. So suppose I have a domain like this, a domain like this. So this is your first node. This is your second node. This is your third, fourth, fifth, and sixth node. So there is nothing. This is the boundary node. This is the boundary node. There is nothing here in the west of here. So this term is not possible. So that means coefficient of C1 is 0 here. We can say trivial for trivial solution. C1 is equal to, as well as this is always the first node. This will be always that C1 will always be 0 because there is no left. And Bn will be 0. B at the nth node. You put I is equal to n. So B at that is the last node here, sixth node. If you go n is 6 here, so you can say B of n will be 0 because there is no east node for that. Suppose your point of consideration is this here for this boundary node. There is no west node. For the point of consideration for this, there is no east. Now, if you go for I is equal to 2, or how much will be, you can say D1, T1. You can say A1 will be, if you want to find at I is equal to 1, A1 will be 1, B1 will be 0, C1 is also 0, okay, and D1 is equal to nothing but T1. So D1 is almost many with the T1. Now, for the I node 2, for node 2, this was I is equal to 1. Now suppose I is equal to 2. So that means the equation will be A2, E2 is equal to B2, E3, the east node, C2, E1 plus D2 plus T. Now here, if you see, T2 is also unknown and T3 is also unknown. Initially, the boundary condition was known. But here, T2 and T3 both are unknown. That means T2 is nothing but a function of T3 and some constant. Because here T1 is known. T1 is known because of the boundary condition which we have given as a Dirichlet boundary condition. So T1 is. So T2 is a function of T3. T2 is a function of T3 and some constant. Similarly, if you go for I is equal to 3 node, I is equal to 3. That means A3, P3 is equal to B3, this node of third, C3, west node of third, plus B3. Again, if you see, this is unknown, this is unknown. Okay. Am I right? Okay. So similarly, again, if you see, E3 is nothing but function of what? E4. So, all. Okay. Now, similarly, if you go for nth node, so n minus 1 first, n minus 1 node, an minus 1, that is, or you can directly say that Tn minus 1 is nothing but function of next T of n and some constant. And T of n will be function of T of n plus 1 and so on. So that means you have forward substituted the values here. When you were putting the values, that was forward substitution. Substituting. Because when you saw Initially, T1 was known. T1 was known. So from that, T2 was nothing. T1 was known, so D1 we got. Okay. So then T2 was unknown, T3 was unknown, T1 was known. So T2 was a function of T3. Okay? And T3 was a function of T4. Tn minus 1 was a function of Tn. So it was forwardly substituting. And Tn is a function of Tn plus 1. So here you obtain the value of Tn. You obtain the value of Tn because again it is a bounded one. Okay. Okay. Now, if you know the value of Tn from here after solving, okay. So if you know the value of Tn, you can get the value of Tn minus 1. I hope you all are getting that. So what I'm trying to say, Tn, we got the value directly from after solving the last equation. Okay. All right. So you put the value of yes. You put this value in here, you get Tn minus 1. You put this value again back, you get that Tn minus 2. Similarly, you will get T4. If you put the value, you get T3. Similarly, if you put the value T3, you will get T2. So that is called as back substitution. That is called as back substitution. Back substitution is back substitution. Okay, that is back substitution. All right. Pretty simple case. It was nothing challenging. So what TDMA do here is that this TDMA so this TDMA, if you observed here, it was like T at ith node is nothing but some coefficient Ti, T at the next node plus Qi, the constant value. Okay, constant value. So Ti is nothing but function of Ti plus 1 plus constant value. That was only written here. Because this whole is a, if you see here, T at 2, which was to be found out, is nothing but the next value, T of I is equal to Ti plus 1 plus some constant value which you have. So you can say Tn can be also written as Tn is nothing but T of n plus 1 plus Q of n plus Q of n. Now again, you know that this will be 0 because there is no n plus 1 node. There is no n plus 1. Only the boundary value or boundary condition value that is equal to Q. You know the Tn, you put in the previous step, back substitute, you know, get the value of T of n minus 1. Then T of n minus 2. And similarly, you get the value of at the value of T of. Okay. So what does that mean? P of, suppose if I want, sorry, T of I minus 1. I want to write T of I minus 1 is nothing but P of I minus 1, P of I plus Q of I minus 1. Simple thing. If you are finding this coefficient, this value Ti, the coefficient will be of I and constant will be of I, but here it will be of the next node, that is nothing but the east. Similarly, I have done here. If you are finding the coefficient of I, value of I minus 1, coefficient of I minus 1, constant of I minus 1, and the value of the east. Next. Okay. Got it? Now, What we can do here is that suppose we have this equation named as equation number 1. This is the equation number, suppose this is 2. All right. Now, if you put the values here, just a second. So your equation for I is nothing but A of I, okay, P of I, which we have wrote earlier, is equal to B of I, P of I plus 1, plus C of I, P of I minus 1, plus P of I. Okay, this was the equation which we have done already. This equation, this one, I've only written again. This equation I've only written again. Now, if you put this T of I minus 1, this T of I minus 1 in here, that is A of I, P of I is equal to B of I, P of I plus 1, plus C of I. P of I minus 1 is P of I minus 1, Pi plus P of I minus 1, P of I minus 1. Okay. Sorry. That is only we are substituted. Plus P of I. Now let us expand this. When we expand this, we will take out the coefficients of I on the left hand side, I plus 1 on the right hand side, and the remaining also on the right hand side. So what do I mean here is that P of I we take out. This is the coefficient of P of I. This is the coefficient of P of I. So P of I is nothing but A of I minus Ci minus Ci P of I minus 1. And I plus 1 coefficient is as it is, B of I, P of I plus 1. Okay. And remaining Ci, P of I minus 1 plus Bi plus Bi. Okay. I hope this much is clear. Now what we will do, we will take PIS, we will transpose this over the right hand side. Pi will be nothing. P of I plus 1 coefficient will be Bi over Ai minus Ci, P of I minus 1 plus how much? Pi plus Ci Qi minus 1 over Ai minus Ci P of I minus P of I minus. Now, this, let us say this equation is number. Now you compare this equation number 1 and equation number 3. Same equations. Equation 1, Pi is equal to Pi Ti plus 1 plus Qi. And equation 3, you will get the values of Pi and Qi. Compare. Equation 1, and if you compare it, just take a minute and compare once. Okay, I guess you have compared. Okay, so if you compare what you get, okay, okay. I guess you might have compared now, right? Okay. So if you compare, PI will be how much? PI over AI minus PI, PI minus 1, and QI will be PI plus CI, QI minus 1 over AI minus CI, P of I minus 1. P of I minus 1. All right. Dinesh, I'm audible? Hello? Okay. Okay. Hello, I'm audible? Okay. Return yes. Chal. Okay. All right. So we are discussing about the TDMA scheme, Dinesh. So we got PI and got PIN pure values. We got the PIN pure values so far. Now it is a recurrence relation for PIN because you know the PI minus 1, you know QI minus 1. If you put suppose I is equal to 1 here, I is equal to 1. If you put I is equal to, so P1 will be B1 over A1, and you know that C1 was 0. C1 and B1 Bn are 0 for trivial solutions. And Q1 will be how much? D1, C1 is 0, A1, D1 over F, D1 over. And these A1, B1 are you will get from the discretized coefficients of the equations. We will solve that thing, don't worry. Similarly, if you put I is equal to 2, I is equal to 2. So P2 will be how much? B2 over A2 minus C2, P1. So you know P1, you know all the other coefficients B2, A2, C2 from the discretized. Similarly, Q2 will be how much? P2 plus C2 Q1 upon A2 minus C1 P1. So you know Q1 and P1, you again got the Q2. You again got the Q2. Right. Now Pn will be, if you go with the Pn, I is equal to N. So Pn will be 0 because Bn is 0, triple. Bn is 0. And Qn will be Bn plus Cn Qn minus 1 upon An minus Cn Cn minus 1. I wrote something wrong here. It will be C2. Okay, Tn max. Now you know that Tn is nothing but Qn because our equation is what? Pi is equal to Pi. What is the equation? Pi minus 1, Pi Ti plus 1 plus Q1. When you put n, I is equal to n here, I is equal to n here, then Tn will be nothing but Pn is 0, P of n plus 1 plus Q of n. Pn is 0 because Bn is 0. That is nothing but Q1. Pn is nothing but. So you can say that P1, Q1, P2, Q2, all the values are known for nodes 1 to n. We got the values of all the nodes. Therefore, PQ values, PI, QI values for I is equal to 1, 2, up to n are known. Are PI, QI values are known. Okay. Now you will start the back substitution. Now you will start the back substitution because you got the value of Pn. Now you got the value of Pn. The P of, if now I is equal to n minus 1, I is equal to n minus 1. So what will be P of n minus 1 will be P of n minus 1, P of n plus Q of n minus 1. So this is known. This is known from here. This is also known. Therefore, T of n minus 1 is known. That is the back substitution happening. Back substitution. Now you start getting all the values. Similarly, for I is equal to 2. So T2 is nothing but P2, P1, or T3 plus Q2. So this is known, this is known, this is known. Got this. Okay. This is so simple. Here. So we can write the Thomas algorithm in a concise way. Thomas algorithm or TDM है. Dinesh, everything is visible. I hope everything is visible here. I can't hear you. Can you unmute yourself? Hello. I issue, sir. Okay. All right. I hope everything you are getting. If you have any doubts, you place it in the chat box. You have the mic issues. No problem. All right. Now, I was writing the complete algorithm. So what we do first, the first point was we calculate P1 and Q1, the coefficients. P1, that is nothing but B1 over A1, and Q1, that is nothing but B1 over. First step is this. Then the recurrence relation happens where you calculate PI and QI for the other nodes. Next step is recurrence relations are calculated. That is nothing but P of I is P of I over K of I, Pi, P of I minus 1, and Q of I was P of I plus P of I, Q of I minus 1 over A of I minus P I, P of I minus 1. Same thing I've written from here. This relation. This one, when we compare with this one. All right. Now the third, for all the values of I is equal to 1, 2, 3 up to minus 1. And the third step is you get the value of Tn node, that is nothing but Qn. And fourth step is start the back substitution. That is Ti is equal to Ti, Ti plus 1 plus Qn for all the nodes, other nodes. Okay. You got the TN? You start the batch session. This was for 1D. Now, if I want to extend this thing to 2 dimension, I want to extend it to 2 dimensional, 3 dimensional. That can also be a. So concept will be same. First we do for 2 dimensional, then for 3 dimensional. So just give me a minute, guys. Okay. So in the 1 dimension case, we understood from the previous lecture that is Gauss sequence, that you go point by point substitution happens. This it's a Thomas algorithm that in one shot you get all the values. TDM. Now, so let's extend 2D. Let's extend 2D. So our equation is nothing but for general AP 5P is equal to summation of A of neighboring nodes, phi of neighboring nodes plus B. This equation we have seen in our previous tutorials as well. So you guess the value, starting value, then you update the latest available value for Gauss signal. For Gauss seidel, initially you guess, so that is 5P is nothing but summation of A and B, phi and B star plus B over AP. You guess the value, and then you update the latest available value. That is phi and B star is nothing but latest updated value. Latest available value. Now in 2 dimensional, the Gauss seidel is pretty much low. Because information travels here cell by cell, from one cell to another, then to another. And you see the boundary conditions are happening as per the iterations. Okay, so multiple iterations happen. So Gauss seidel, you can say that is slow to converge for 2 dimensional, 3 dimensional problems. You can write Gauss seidel slow to converge for 2D and 3D problems. 2 dimensional, 3 dimensional. So what we can do, we can use the combination of PDMA and Gauss seidel to solve for higher dimension problems. Therefore, use the combination of PDMA, Gauss seidel to solve higher dimensional problems. So what actually in CFD we are doing using a finite volume is that we create a domain, discretize it, solve it to get the put the values and get the set of algebraic equations, that is Ax is equal to B form. So, discretize those equations, PDs into an algebraic equations. Now we are understanding that how these equations will be solved in using the computers numerically. So Gauss seidel we have seen, PDMA we have seen in the one dimension. Now for two-dimensional or three-dimensional, use a combination of both PDMA and Gauss seidel to solve these algebraic equations. This kind of method is called as line by line method. Okay? This is known as line by line method. Line by line. So here, suppose you have a grid. Okay. The purple grid. Horizontally, I'm making with the white color. Okay. These are the nodes. So these are the nodes. So your cells will be somewhat like this. These are your control volumes. This is the control volume of consideration. Okay. Okay. So this has the point P. Your control volume of concentration. This is your point P. This is west node. This is east node. This is north node and this is south. This is y direction. This is. So what we do, we apply TDMA in the y direction and Gauss divergence in the x direction. TDMA we apply in y direction and Gauss seidel in x direction. So what does that mean? What is happening actually? In the y direction, the information is propagating as well as in x direction also. But in one shot, you are solving a single column. That is the purple lines in the y direction. And you are getting the updated values when you are sweeping. Okay, there are two terms which you are going to use: traverse and sweep. Traverse and sweep. So traversing in the y direction and sweeping in the x direction using the updated values. Let me write these two terms. Traverse direction is nothing but PDMA y direction and sweep direction is nothing but lines are, you can say, visited in x direction. lines are listed in Excel. So these are the values which are known initially because you guess, and the values on the, you write it here. So these are the values which you know initially. Okay. And the values here are unknown. These are unknown. So what you are doing, values of the X are known. As soon as you get the initial get the values from the Gauss series, you put the updated values. You start with this cell. Suppose if you start with the cell of consideration, get the value. You get the value from the updated value from here. You get the updated value from here. That is not happening. You are traversing in the y direction for the unknowns for the green circle, and you are sweeping in the known values of the sweeping in the x direction. Sweeping in the x direction. So you can say that the cross values assumed to be known, and the dot values are the unknowns. Are the So what we are saying, traverse direction is the direction is the TDMA is applied. So, and in this case, if you see the y direction happens to be the traverse direction, and the sweep direction is nothing but the direction in which the lines are progressed. Okay, from left to right. So let us say in this case, we move from x minimum to x maximum, x minimum to x maximum. We go from zero value to x maximum. So we are sweeping in the positive x direction. We are sweeping in the positive x, positive left to right. Okay, x minimum to x maximum. So this is essentially the direction in which the Gauss-Seidel lines are visible. Gauss-Seidel lines are visible. But initially they are assumed, values are assumed, and then they are getting updated as soon as you get the values of the unknowns. So now the question arises, how do I solve TDMA along these lines? Very simple thing. How you will solve the TDMA applying the y direction. So if we look at the discretized equation which we have made, which was in terms of ij, will be in terms of ij because it's a two-dimensional. Let me write this equation here. The equation will look like Aij. We have already seen for two-dimensional. We have solved the question in previous tutorial. Phi ij is nothing but Aij plus 1, that is north node. Phi ij plus 1. Ei j minus 1. Phi I j minus 1. South node. On the west node, east node. Pi plus 1. J. Phi I plus 1. J plus, this is the east node, west node. Pi minus 1 j. Phi I minus 1 j. Plus some constant Vij. Okay. So you can say left hand value, that is west nodes and east nodes are known. These are also known. You assume that west and the east values in the x direction. In the x direction, all the values are known. In the y direction, you don't. You don't. So that means these are the assumed values. You have assumed it in star. So that means I'll put a star for the east and west nodes. These values are known. So what will happen? This whole will be a constant value. That is nothing but a Gij. You can find. That is known. So how I can write the equation again? Aij phi ij is nothing but Ai j plus 1 phi I j plus 1. Because in north you don't know. Bi j minus 1 phi I j minus 1. In the south you don't know because you are traversing. If this is I, this is I plus 1, I minus 1, comma j, I comma j, I comma j. This is I, j plus 1, I, j minus 1. You don't know the values of I, j minus 1, I, j plus 1, but you know the known values of I minus 1, j and I plus 1. And you will put it here, g of h, g of. Okay, pretty simple. Now you will go from I is equal to 1 to I is equal to n again. I is equal to 1 to I is equal to n. Because our question was that how to solve these in PDM. So as our equation was in terms of ij, if we indicate I and j as the p cell which we have seen. So ij, phi ij would be known for the cell. East and west nodes are known. North and south nodes we need to find. So if you want to apply the TDMA in the y direction, it means that the coefficients A, B, C, D, the coefficient A, B, C, D, which you have written here, A, A, B, C, D, okay, would be unknowns. So if you want to apply, you want two values you need to assume. So similarly, you can go for the three-dimensional case also. Okay, you can go for three-dimensional case. I hope it is simple. Any doubts? Do you have? Any doubts? Have you seen the lecture videos? You have seen? No. Okay. That's it. So also do see lecture videos because it's pretty simple. Just you have to understand once. You understand this thing, and definitely you will able to absorb this. So I'm just giving a brief of what has been done on in the Week-5. And you solve the assignment based on that. Pretty simple. Question has been asked. All right. So for I to 1 to n and similarly j1 to n, you can call for TDMA, and you can check for the convergence. So what we can say that line by line method is pretty fast. Because the first in one go completely solve the complete column in one go. Then you update the values of this, get the updated values. So in this, you solve this column. Suppose you assume these values here, you solve this column completely. Okay. You solve this column. Now you shift to the right side in the x direction. You get the updated values here. From TDMA, you take these TDMA values and assume it to be as a Gauss seidel, because it's a Gauss seidel in the sweeping. And again, you solve this column using TDMA, using this updated values of the Gauss seidel process. Similarly, you again get these values, you again put here, and you can get for all the cases. So this is a combination of TDMA and Gauss seidel. All right. It is a faster method in 2D because the boundary condition information propagates at once to the integers. Let me write some comments here. Line by line method is much faster than Gauss seidel in 2D because the boundary condition information boundary condition information propagates at once to the interior cells. Okay. Next comment B is that. So you can say that this method converges faster. Therefore, LBL converges faster. Now, transverse and sweep directions can be interchanged as well. Okay, then we have assumed that transversing in the y direction and sweeping in the x direction, these can be interchanged. It is not fixed. I think second point, traverse, sorry, not transverse, traverse, sweep, directions can be interchanged. You can transverse in x direction, sweep in y direction. What do I mean? Suppose I have a grid. If you were doing sweep here, traverse here, you can do another way also. You can do traverse here. You can do sweep. So geometry and the properties would dictate the direction of traverse or sweep. Third point is that which direction should be traverse and which direction should be sweep. We can interchange, but how you will identify? So geometry and the properties would dictate the direction of traverse or sweep. Traverse. So what do I mean? Suppose you have a uniform grid. The shape is suppose, or the geometry is suppose uniform. Now how the property will affect? First, let's understand how the property is affecting. Let's understand. Property is affecting like uniform grid. So suppose gamma of east and gamma of west the conductivity, or you can say suppose it's is much greater than gamma of north and gamma of south. So what you can say, the influence of the coefficient nodes AW and A east will be much greater than coefficients of A north and A south, right? North and A south. So what you can say, it can traverse along because east and west are quite influential. Properties of the east and west nodes are influential. So what can we say? Where should I traverse or where should I? You tell me, Dinesh. Dinesh, are you there? I think you are there. Now you tell me, uh, where should, after understanding this thing, where should I traverse and where should I uh, sweep? Think and tell. So traversing, traversing, yes, traversing east. Correct. Traversing. Because the influence of the properties in the east and west are both. You will traverse an east and sweep in, sweep in. East means X direction. Okay. Traversing X direction and sweep in Y direction. Sweep in. Okay. Now, how the geometry will affect? How the geometry will affect? Interesting. Suppose the aspect ratio is quite different. It's not a uniform grid that X and Y have the same dimensions. The grid looks like something like this. Okay. And here, so if you observe, X dimension is quite higher than the Y dimension. See, our cell of consideration is this. So this is the east node. This is the west node. This is north node, and this is, suppose this was your del X. Whole cell X direction is this much. This is del Y. Del X to del Y is quite non-uniform. This will be how much? Del Y south, and this will be how much? Del Y north in that direction. We have seen all these geometries in our previous tutorials, okay? So please don't get confused. And this will be how much? Del X west. This will be how much? Del X east. Okay, del X east. So you see, X dimensions are quite large. Okay. Now, if we write the coefficients, so A east is written as gamma E over and delta Y over del X east. We have seen this already. And A west will be written as gamma west delta X. Sorry, in north I should write. To compare gamma north delta X over delta YN. So we know that since del XE is much larger than del Y naught. So this will be higher, this will be smaller. This will be smaller and this will be a higher value. This will be. What we can say that AN is greater than the east. AN north is influence of north is greater than what we can say. We will traverse in Y direction because in north the influence of north is this time higher than the east and west. So we'll traverse in Y direction and sweep in X direction. Therefore, traverse in Y, sweep in X direction. Okay, I'm audible right now. Sorry, actually, for some technical issue. All right. Yeah. So let me share my screen once again. Yeah. Okay. Dinesh, I'm audible. Hello. I hope I'm audible. Okay. Okay, I'm audible. So yes, we're back again. All right. So I was saying about that the influence of the north and south nodes is much higher than the east and west nodes. Okay, because of the geometry. Because of the geometry. So we basically bring the known values. Also following the Gauss sequence. All right, let's do a short question on it, or we can understand about the linearization of the terms also. Those terms, because we have been told in the previous lecture that we just take the linear source term, but how to linearize those source terms is the case. But before, I think we can do at least one question for coming to the linearization part, or at least 1D we can do that, or to solve it with linear. Let me do one question here. So this is a one dimensional point A, okay, that is having 100 degrees Celsius, 1D diffusion I'm doing. And at this point, the temperature is 400 degrees Celsius. Is that the boundary node say? Let me again write A, the boundary node B. Okay. This temperature, this boundary is maintained at 100 degrees Celsius. This is maintained as 400 degrees Celsius. These are the nodes 1, 2. This is a 1D steady diffusion case. 1D steady diffusion case. 1D steady diffusion case. Strength. Yeah. Okay. Yeah. So here source we have assumed as to be 0. Gamma we consider as 1 watt per Kelvin. Spacing between them is assumed to be 1. Just checking if it is 1. So between each node it is 0.5, 0.5 from the faces. Area suppose it is given to be 1 meter. Using TDMA. So for cell 1, you go AE is nothing but gamma EAE over del X E. Okay. So gamma is 1, A is 1, del X E is 0.5. So that is, sorry, Del x e is 1. That is 1. Okay. This del x e for the first is for finding the east value. Similarly, for the west value, how much it will be? West value, the coefficient of west value. You get the value. Okay. If I go for the cell 2, so what should I write the west value? Can you tell me, Dinesh? A west is nothing but gamma w a w over del x x w y 2, because the west node itself is the boundary node for cell 1. So 1 into 1 over 1 over 2. That is what will the equation number 1 solve? How I can write the equation? To write the equation, should I not write the equation? Let's come to cell 2 first. Okay. So cell 2 is A east again, and is gamma east A east upon del x east. This one, but A west will also be, because for the node 2, for the node 2 west node is this one. Gamma west A west over del x w. This will be also 1. The equation will be something like A2 T2 is equal to A1 T1 plus A3 T3. That is the only case. So A2 is nothing but how much? 2 times A1 plus A3. So 2T2 is equal to T1 plus T3. You go for cell 3 again. That will be how much? Think we have done these equations already. Okay. So cell 3, we should go for cell 3. Then again, A west will be 1, but A east will be how much? Gamma E upon del x e by 2, because that's a boundary node. That will be again 2. The equation will be 3 plus 1 T2 plus 2 into 400 into 400. That's a constant value of the temperature. The equation will be 3T3 plus T2 plus 800. You have all the three equations with you. First equation is similar here. I've not written the equation. Okay. So 3T1 is equal to 3T1 is equal to 1T2 plus 100. Sorry, 200, 2 into. You have all these three equations. Equation 1 is, now the thing is how to solve using PDM. You have made these equations. We have already done solving, framing these equations. Okay, after discretization. 3T1 is equal to T2 plus 200. 2T2 is equal to T1 plus T3. 3T3 is equal to T2 plus 800. Now, what was the equation of our generalized equation of TDMA? AI EI is equal to BI east node plus CI west node plus DI. So here PI or P1 is nothing but P1 over A1. P1 over A1. You see from the first equation, This is node 1, node 2, or I should write I is equal to 1, I is equal to 2, and I is equal to 3. Then I is equal to 1 here. So P1, first step for Thomas algorithm was the first equation you see B1 is the coefficient of the next. So if you are finding T1, the coefficient of this is 1. 1 over A1 is how much? Coefficient of over 3. And Q1 was D1 over A1. So D1 is 200 here, constant value from the I is equal to 1 equation, and A1 is 3, 200 over 3. Now, you know for the internal nodes, the equation is Pi, the values of Pi and Qi is written like this: Bi over Ai minus Ci, Pi minus 1. And Qi is nothing but Bi plus Pi, Qi minus 1 upon Ai minus Ci, Pi minus 1. Right? So if you put I is equal to 2 this time, I is equal to 2. So P2 will be how much? P2 over A2 minus how much? C2 P1. And Q2 will be P2 plus C2 Q1 over A2 minus C2 P1. You know P1, you know Q1. You know the value of B2, A2, C2 from this equation of 2. Okay. If you put B2 is how much? 1. A2 is how much? 2. B2 is 1. To see this equation. If you're finding for 2, B is the coefficient of the next one, C is the coefficient of the previous one. And A2 is the coefficient of itself. 1 upon 2 minus 1. And P1 you have calculated as here 1 by 3. So that is 3 over 5. This is your P2. Similarly, Q2 will be how much? D2. What is the coefficient D2 in the second equation? There is no constant value, sorry. 0 plus C1 is C2 is 1 into Q1 you have calculated as 200 over 3. 100 over 3. And how much is A2? A2 coefficient is 2. Minus C2 into P1. That will be P2 is how much? 1. Okay. Yes. P2 is 1. And P1 is how much? We have calculated as 1 over 3. So that will be 200 over 3 upon 5 over 3. That is 200 over 5. That is 40. Q2 you got. Similarly, you can get I is equal to 3. Put I is equal to 3. So you will get P3 and Q3. So P3 will be 0 and Q3 will be, after putting the values, will come out to be 800. I hope. 800 plus 1 into 40 over 3 minus 1 into 3 by 5. That is 3. We got Q3. Q3 is the T3 itself. So Tn is equal to Qn. We did that. So Q3 is 350 degrees Celsius. We got T3, start the back substitution. Start with the back substitution. Take 2 minutes and tell me after back substitution what will be the values are T1 and T2 and compare with the analytical part. Take 2-3 minutes and tell me. Okay. Okay, I guess after substituting, you might have got the values. So, Dinesh, can you tell me what is T1 and T2 coming? What is the value of T1 and T2? So T1 is given to you guys. What is T2 basically? From the equation, you can put directly values and you get the values of T1 and T2. Okay, T2 is 250. All right, let us see. So you know the back substitution, T2 will be, T2 is how much? What was the equation of T2? T2, T3 plus Q2. T2, T3 plus Q2. So P2 is how much? You have calculated 3 by 5. T3 you have calculated 350 and Q2 you have calculated as 40. So this one gets cancels 70 to 1 plus 40, that is 250 degrees Celsius. T1 is equal to how much? T1, T2 plus Q1. So P1 was how much? P1 was 1 by 3 and Q1 was 200 over 3. 1 by 3 into 250, 200 over 3. 450 by 3, 150 degrees Celsius. So T1 also you got. Okay? T1 is 150, T2 is 250 and 3 degrees. Now the equation, one analytically we will, let's verify. So if you see the equation is 1D diffusion equation. D by dx of k dt by dx, no source is equal to 0. Integrate it one time. What you get? K dt by dx is equal to constant. That is C1. Again integrated. T is equal to C1x by K plus. Okay. This is your equation of temperature. Now you know that x is equal to 0. At x is equal to 0, temperature at A in the question is given as 100 degrees Celsius. Put x is equal to 0, boundary conditions, and x is equal to L, that is 3 meters. T at B is given to be 400 degrees Celsius. Put the values. X0, so 100 degree is equal to 0 plus C2. So C2 is 100. X is equal to 3, 3 is 400. 400 is equal to C2, C1 by K. C1 you don't know. C1, K is 1, 3, plus C2 is 100. So 400 minus 100, 300 by 300. So C1 comes out to be 100. So equation is P is equal to C1 by K, that is 100 by 1 x plus C2 is 100. So that is 100 into plus 1. This is your equation. Now you get the values at all the points. So T1 x is equal to 0.5. T1 will be 100 into 1.5. That is 150 degrees Celsius. Correct. X is equal to 1.5. You will get T2. How? If you see the figure, this was the figure. This is 0.5. Okay, because this is complete one. This will be how much? 1.5. So X is starting from here only. Your origin is here only. So T2 will be 100 into 1.5 plus 1. That is 250 degrees Celsius. And X is equal to 2.5. T3 will be 100 into 2.5 plus 1. That is 350 degrees Celsius. All the values are matching from analytical solution. I hope it is clear. Is it clear, Dinesh? Or any doubts? Is it clear? Okay. Yes. Okay. All right. Now let's come to the linearization of the source terms. Because we have done that case in previous tutorial that we were just writing the linear form of the source term. But what if the source term is dependent on square, cube terms as well? Let me write the heading. Source term linearization. So suppose your source term is dependent on temperature T, variable T, which is function of either T square, T cube, and so on. So you have to linearize this source term by, and it is recommended that you use Taylor series. Recommended to use Taylor. So you know the values T star and S star will be the previous iterated values. Okay, I'm writing this previous iterative values, previously iterative values. So what you can say, S is nothing but S star plus by Taylor's expansion ds by dt of S star into T at P minus T at P star. Only the first, because we are getting the higher order terms. Linearized. Suppose we take examples. We have a source term. We have a source term such as f is equal to 4 minus 5t. This is a source. 4 minus 5. So S star will be how much here? That is 4 minus 5t star cube. And ds by dt will be how much? Minus 15 star square. So after linearization, S will be written as 4 minus 5t cube S star plus ds by dt into t minus t star. Minus 15 t square into t minus P star. Okay. So this is your equation. So it will be like 4 T cube. I'm audible. Hello. Ah, it's connected. 4 plus 10 T star cube minus 15 T star square to T. Just expanded this expression. Solve this expression. And I got this value. That is nothing but I want to say it is a for at a point P. So this is 4 plus 10 TP star Q minus 15 TP star square into your source term is written like this is your SC constant value and this is your SP TP. SP. All right. So your SC is because how we write that? S is nothing but SP plus SPTP we used to write. SC is 4 plus 10 TP star Q and SP is nothing but minus 15 TP star. And SC and SP need to be updated at every iterative step. Okay, because these are the iterative guess values initially. Okay, you need to update it. Okay. SC and SP need to be updated with iterations. Or now, second case can be like one case was that you have a constant value as a variable, ST and SP both were. Second case will be like your source is nothing but S is equal to 4 minus 5 TP star cube, where SC is this and SP is 0. Okay. So it's a lazy person's approach, we can say. So, and it will be slow to converge, and the diagonal dominance could be affected here. Diagonal dominance. In this model too, you can say that you have a source which is SC plus SP, SPTP. SP is 0 here, and SC is 4 minus 5 TPQ. So you can say that we can dump all the source term into a constant value. The lazy person approach, when you dump the source value to be a constant, it will converge, right? But it will converge very slowly. Because we are not using the correct value of this source. Okay. All right. So we understood about the Scarborough criteria here. It will satisfy the Scarborough criteria or not. Diagonal dominance can be affected there. The third case can be, let me write here, lazy approach. Diagonal, no convergence, no convergence diagonal dominance be affected. Yeah. Now, suppose we have a third case, third model, where your SC is 4 and SP is minus 5 TP stars. S can be written as SC minus 5 TP star square T. SC plus SPT. So the example 4 minus 5 TP. 4 minus 5 TP square star square T. So if you observe that here, the slope is nothing but SP. For any linear equation, SC is equal to SPTP. So S and TP are the axes, S and T. So if you see, this is a constant value, this is a y is equal to mx plus c. This is your slope, SP is your slope. So here SP is minus 5 TP, minus 5. And in earlier case in the model 1, you observe, your slope was minus 15, minus 15. So slope is a bit less steep slope, less steep. The slope less steeper. So it is also again slow to converge from the actual case, slow to converge. So the actual case was this. This was your actual case. Then you put the star values and got this from the actual case. In model 2, you assume that SP is 0, lazy approach. Third case, you assume that SP is slope or other SP is less. So again, it will be slow to converge from the actual case. Slow to converge. Does not account for the fall of S with T. And does not account. Slowly it will converge, so not necessary that the convergence rate will be high. Another case can be like that when SP is greater than 0. If you see here all the values here, SP is negative, negative 5 TP square or negative 15 TP square. SP can be showing a positive value. Example, if SP is 0 or SP is greater than 0, so SC can be suppose like negative 100 plus ST or plus 5T. Okay. Okay. SP is greater than 0. So now let us plot all the values on the graph. I hope everything is clear to you. Just absorb, take a minute or two. Okay. So what is happening? Suppose I draw the graph. Okay. Source versus time. Temperature. Okay. Suppose your value was going like this. Now you see the slopes here. When SP is less than equal to 0, negative value. Suppose at a particular point you draw in, get a value of actual value of this. Okay? Get the actual value like this. My slope is negative, or slope actual value is this, but if the slope is negative after linearization, or slope is positive, how it will affect? A negative SP gives a positive slope. Negative value SP gives a positive slope. That means it will be something like this. Violate SP, violate SP less than equal to 0. So SP is positive. SP is positive. That means it is violating. The source is acting like a system, which is not possible. That means internally the uh, energy is being created on. This is not possible. So the first model was you had a tangent. This was the first model actually. Second model, you said that slope is only constant value. It is a constant value. Okay. This is your constant value in the model 2. The model 3, you said that slope is less steeper. The tangent will look like something like, can look something like what? It's less steeper. Let me make this again. So less steeper means something like this model number. This was model number. This is how you can see the linearizations of the plot in the plotting format. Okay. We have source term on the y-axis, temperature on the x-axis. So curve is the model, this blue color. Okay. So 4 minus 5t cube is the actual source term which we had here. 4 minus 5t cube start value. This source term is nothing but 4 minus 5t cube. I draw the tangents over that. Using the first model of the linear, using Taylor-Series expansion, it will change the slope. Once you make the constant value, then another view is the less slope value, and last case model can be like that if you have a SP which is greater than 0. That will violate your actual resource. Okay. The final equation was S is equal to S star plus S by rho T star T minus at point P. All right. Okay. I guess this is all for today. We have discussed a lot about EDM and linearization of the source terms and how to solve that one, the diffusion equation using TDM. So I think that's it. If you have any doubts, please let me know. Any doubts to anyone? Please, you can raise your hand. You can tell me. All clear? Doubts? Okay. All right. Great. So I would request you all that you continuously follow the lectures, okay? And also be regular to your assignments and kindly join the lectures. Okay. It's all from my side. Hope I was able to make things clear about TEMS scheme, what is the algorithm of TDA, how you calculate do the substitution, forward and back substitutions. You can convert it to 2D as well. You use the line by line method. It's a mix of Gauss divergence, Gauss seidel and uh, TDMA, where you also understood about the traverse and sweep directions, how they are being affected about the properties and the shape of the grid. Then we did one question here. All right. And finally, we came to the generalization of the source terms. We picked one model uh, and how to expand it linearly using the Taylor series expansion. We plotted all the values of the source terms with the Taylor series. Okay. Okay. Yes, I think we can end the meeting. If you have no doubts, you can. Okay. Yeah, welcome the next one. All right, no doubts. So I think I can end the meeting for all of you. You can leave them.